Let us look at some industrial aspects of separation of biomolecules. We have been talking about biotechniques, which are techniques that are useful in separation, purification, and quantification of biomolecules. So industrially, we need to just have a snippet of what happens, um, or how processes are, aligned, made into unit operations, and so on. So the content of this is an introduction, material and energy balances, material handling and related preliminary operations, mechanical separation, theory and applications of membrane separation processes, theory and application of contact equilibrium separation processes, and food freezing. So we are using food processing as an example to look at industrial processes. To start us off, we have the basic principles of unit operation in food process engineering. So the study of process engineering usually attempts to combine all forms of physical processes into a small number of basic operations that we call unit operations. For instance, if you look at food processes, they may seem, so much and bewildering in their diversity, but careful analysis will show that these complicated and differing processes can actually be broken down into a small number of unit operations. For example, consider the processes of heating. We normally have to do many innumerable instances where we have to do heating in food industry. There are many reasons for heating and also cooling. For example, maybe you want to bake bread, you are freezing meat and food, you are frying yam slices in oils, etc. But in process engineering, the prime consideration will be now, first, the extent of heat or cooling that is required. So we first consider it as how much of heating or cooling is required. Then number two, the conditions under which this must be accomplished. So how do we achieve that extent of heating? How do we achieve that extent of cooling? Thus, this physical process qualifies to be a unit operation. So we don't break it down into baking of bread, freezing of meat, frying of what. We're breaking it into what is the heat capacity. Do we need 4 degrees? Do we need 60 degrees, 100? And then how do we achieve that? What maybe instrumentation do we need to achieve that? So this makes it a unit operation. So all engineering deals with definite and measured quantities, and so depends on making some measurements. So to make a measurement is to compare the unknown with the known. For example, you're weighing a material, maybe amount of sugar. So you weigh and you compare it to the standard weight such as a kilogram. And I think you have seen this even in our shops and other places. So the result of the comparison is expressed in terms of multiples of the known quantities. For example, how many kilograms in this particular example. Then we also need to do dimensions of length, mass, time, temperature, and for convenience in engineering calculations, force is added as another dimension into now the length, mass, time, and temperature. Force can be expressed in terms of other dimensions, but it simplifies many engineering calculations to use force as a dimension. For example, we say weight is equal to milligrams. So several dimensions are represented by symbols. Maybe length we do L, mass we have M, time we have small t, temperature we have capital T, and force we have F. Note that these are enclosed in square brackets, which is the conventional way of expressing dimensions in industrial processes. Then we have units. So dimensions are then measured in terms of units. For example, the dimension of length is measured in terms of length units like micrometer, millimeter, meter, kilometer, etc. So that the measurements can always be compared. So the units have been defined in terms of physical quantities. For example, the meter can be defined in terms of the wavelength of light. A standard kilogram has also been described as the mass of a standard lump of platinum iridium. Then the seconds in time is the time taken for light of a given wavelength to vibrate at a given number of times. Yeah. Now, material and energy balances. So, material quantities as they pass through food processing operations can be uh, described by material balances. So, any material quantity that is going through this process, like now in food processing operations, can be described by material balances. Such balances are statements on the conservation of mass. Similarly, energy quantities now can be described by energy balances, which are now statements of the conservation of energy. If there is no accumulation, what goes into a process must then come out. Yeah. So this is true for batch operation. When you're having batches, maybe you have batch 1 of cooking oil, batch 2, batch 3, etc. So this is true, and it is equally true for continuous operations over any chosen time interval. So material and energy balances are very important in the food industry. So material balances are fundamental to the control of processing, particularly in the control of how much yields of product, and the needs to be reviewed periodically. So we have materials being put into a process, and then how much material comes out at the end. What's the balance of material? What's the balance of energy? In short, how are we able to conserve the mass? Because whatever input you do within a process, then you need to also compare with whatever the output for both materials and also energy. So the basic principles of material or mass and energy balances. So if the unit operation, whatever its nature is seen as a whole, it may be represented diagrammatically as a box as shown, as I'll be showing you in figure 1. So the mass and energy going into the box must balance with the mass and energy coming out. Otherwise, there will be issues of reduction in mass, loss of energy, and all that. Yeah, so this is what we call mass and energy balance. So we have the raw materials that are coming in, and we also have the energy coming in. For example, heat, work, chemical, even electrical energy. Then within the unit operation, we have the stored materials and the stored energy within that particular process. Then we have products that will come out. We have waste products. We have energy in products. We have energy in waste, and we have energy losses to the surrounding. So this inputs must balance the outputs, mass and energy balance. So material handling and related preliminary operations. At the time of harvest or slaughter, most foods are likely to contain some contaminants, to have components which are inedible, or to have variable physical characteristics, for example, shape, color, sizes, and it is therefore necessary to form one or more of the unit operations such as cleaning, sorting out, grading, peeling to ensure that foods with uniformly high quality are prepared for subsequent processing. So this is now what we call material handling and preliminary operations. So cleaning is a unit operation in which contaminating materials are removed from the food and separated to leave the surface of the food in a suitable condition for further processing. We can have peeling of fruits and vegetables, skinning of the meat, and descaling of the fish may also be considered as a cleaning operation. In vegetable processing, we have blanching that also helps clean the product. The presence of any foreign contaminants in processed foods is the main cause of prosecution of food companies because it poses a high risk to actually the end consumer. Cleaning should take place at the earliest opportunity in a food process, both to prevent damage and to subsequent processing equipment by stones, bones, or metals, and to prevent time and money from being spent on processing contaminants, which will then be discarded. So we are saying that this process should occur a bit earlier. So maybe even at collection point to avoid passing it through processes and then still you're wasting energy, you're wasting time, yet those will be discarded. Again, you could also have them spoiling the machines if maybe it has metals, bones, and all that. We have different types of cleaning. We have wet cleaning, which is more effective than dry methods for removal of soil from root crops or dust and pesticide residues from soft fruits and vegetables. It is also dustless and causes less damage to foods than dry foods. Different combinations of detergents and sterilants at different temperatures allow for flexibility in this particular unit operation. We also have dry cleaning, which are procedures used for products that are smaller, have a greater mechanical strength, and possess lower moisture content. For example, when you talk about grains and nuts. So after cleaning, the surfaces are dry to avoid preservation or further drying. The main groups of equipment used for dry cleaning are air classifiers. We have magnetic separators that can remove metallic contaminants within grains, and separators based on screening of foods. We have then another method called sorting. Sorting is a separation of now foods into categories based on measurable physical properties. Like the processes of cleaning, sorting should be employed as early as possible to ensure a uniform product for subsequent processing. The four main physical properties used to sort food are based on size, based on shape, based on weight, and also based on color. Then we have grading. So we have cleaned, we have sorted, now we do grading. This term is often used interchangeably with sorting, but strictly means the assessment of now the overall quality of a food using a number of attributes. So sorting, that is separation based on some physical characteristics, may therefore be used as part of grading, but we cannot sort and assume that we have graded. So grading is carried out by operators who are trained to simultaneously assess a number of variables. For example, eggs are visually inspected over tungsten lights, termed as candling, to assess up to 20 factors and remove those that, for example, are fertilized or are malformed, and those that contain blood spots or rot. So now you can see that physically, if you have the eggs and you are sorting them, you may not be able to tell if they are fertilized, they have blood within them, or they are rotten. But at least now, when you grade, you're able to do that. Then we have what we call mechanical separation. So that was preliminary, now this mechanical separation. So mechanical separations can be divided into four groups: sedimentation, centrifugal separation, filtration, sieving. In sedimentation, two immiscible liquids or even a liquid and a solid that have different densities are separated by allowing them to come to equilibrium under an action of gravity, so that the heavier material falls with respect to the lighter one. And this may be a slow process. It is often speeded up by applying maybe centrifugal force using a centrifuge to increase the rate of sedimentation. Filtration is a process of solids, separation of solids from liquids by causing the mixture to flow through some fine pores, like the way we did membrane separation techniques. So you allow them to flow through, which are small enough to stop the solid particles, but large enough to allow the liquid to pass through. Then sieving, interposing a barrier through which larger elements cannot pass, and it's often used for classification of solid particles. Sedimentation uses gravitational forces to separate particulate material from fluid streams, and the particles are usually solid, but they can be a small liquid droplet. The fluid can be either liquid or gas. Sedimentation is often used in food industry for separating dirt and debris from incoming raw materials, can also separate crystals from their mother liquor, and also dust or product particles from air streams. In sedimentation, particles are falling from rests under the force of gravity. Then now in centrifugation, separation, we have separation of now said two immiscible liquids or even a liquid and a solid depending on the effect of gravity. And sometimes this separation may be very slow because the specific gravities of components may not be very different, or because of forces holding the components in association, which may occur, for example, in emulsion. Then sieving, now in more details, in the final separation operation in this group, restraint, you provide a restraining mechanism where some particles are separated by mechanical screens that prevent them to pass through. This is done successfully using increasing smaller screens to give a series of particles classified into size ranges. So you can use different sizes of sieves to allow different sizes of products. The fluid, usually air, can effectively be ignored in this separation, which is called sieving. Now the material is shaken. Usually you agitate it above a mesh or a cloth screen so that the smaller particles can pass through. Then rates of throughput of sieves are dependent upon a number of factors: nature and shape of the particles, frequency of the amplitude and the amplitude of the shaking and agitation, methods used to prevent sticking and also bridging of particles in the apertures of the sieve, and tension and physical nature of the sieving material. Another unit process is contact equilibrium processes. Biological raw materials are usually mixtures, and to prepare foodstuffs, it will be necessary to separate some of these components of the mixtures. One method of separation is by introduction of a new phase to the system and allowing the components of the original raw material to distribute themselves between the different phases. For example, freshly dug vegetables have another phase, water, added to remove unwanted a mixture of alcohol. You can also add a mixture of alcohol and water. Is heated to produce another phase, vapor, which is richer in alcohol than the mixture. So then different components will dissolve in the different phases, the alcohol, the water. So by choosing the conditions, one phase is enriched while the other is depleted of some components. The maximum separation is then reached at the equilibrium distribution of the components, but in practice, separation may fall short of this equilibrium, having not been attained. The components are distributed between the phases in accordance to the equilibrium distribution coefficients, which give the relative concentrations in each phase when equilibrium has been reached. The two phases can then be separated by simple physical methods such as gravity settling. This process of contact, distribution, and separation gives the name contact equilibrium separations. Successive stages can be used to enhance the separation. So the two features that are common to all equilibrium contact processes are the attainment of or approach to equilibrium and the provision of contact stages. So equilibrium is reached when a component is so distributed between the two streams that there is no tendency for its concentration in either stream to change, like moving between either of the phases. So once we attain an equilibrium, it may take appreciable time, and only if this time is available will effective equilibrium be reached there. So you need to give it some time. The opportunity to reach equilibrium is provided in each stage. So with one or more stages, the concentration of the transferred component changes progressively from one stream to the other, providing the desired separation. Some of these processes include gas absorption, extract and washing, distillation, and crystallization processes. So membrane separation processes are other processes that occur in food processing, and membranes can be used in processes such as reverse osmosis to separate constituents of food on a molecular basis, where the foods are in a solution and where a solution is separated from one less concentrated by a semi-permeable membrane. So water flows through the membrane from the dilute solution to the more concentrated one. The force producing this flow is called osmotic pressure, and to stop the flow, A pressure equal to the osmotic pressure has to be exerted externally on the more concentrated solution. So the osmotic pressure in liquids arises in the same way as partial pressures in gases, using the number of moles of the solid present and the volume of the whole solution. The osmotic pressure can be estimated using what we call the gas laws. So if pressures greater than the osmotic pressure are applied to the more concentrated solution, the flow will not only stop but will reverse, so that now the water passes out through the membrane, making the concentrated solution even more concentrated. This is the reverse of what actually happens normally. The flow will continue until the concentration rises to the point where its osmotic pressure equals to the applied pressure. Such a process is now what we call reverse osmosis, and a special artificial membrane have been made with the required tight structure to retain all but mainly the smallest molecules, such as those of water. We have also distillation separation process for separating components in a mixture by making use of the fact that some components vaporize more readily than others. So when vapors are produced from a mixture, they contain the components of an original mixture, but in the proportions which are determined by the relative volatilities of these components. So the vapor is richer in some components. Those that are more volatile, and so separation occurs. So in fractional distillation, the vapor is condensed again and then re-evaporated even further, so that to continuously keep separating different components. It is difficult and sometimes impossible to prepare pure components this way, but at least you have a degree of separation that can easily be attained if volatilities are reasonably different. But if they are close to one another, then it means that we are likely to have still not very good separation. So if you need very high purity, then you may need to do several distillations. Major uses of distillation in food industry are for concentrating essential oils, flavors, alcoholic beverages, and deodorization of fats and oils. We have another process we call evaporation, and frequently used in the food industry, so that we are able to evaporate the fluid or the liquid and leave the solid particles of the particular food substance. Basic factors that affect the rate of evaporation are the rate at which heat can be transferred to the liquid, quantity of heat required to evaporate each kg of water, maximum allowable temperature of the liquid, pressure at which the evaporation also takes place, and changes that may occur in the foodstuff. And sometimes you don't want to alter the components of the foodstuff. We have another unit operation called food freezing, and it is the reduction in temperature generally by supercooling, where we have supercooling followed by crystallization of water, nucleation, and finally crystal growth. So supercooling occurs when temperature of water is lowered below the freezing point and the crystallization does not occur. The supercooling provides a means of determining the depth effect of a reduction in temperature relative to the initial freezing point. Then the crystallization process is now formation of systematically organized solid phase from a solution or vapor, and this crystallization consists of nucleation and crystal growth. So the former, that is nucleation, is the association of molecules into tiny particles of size sufficient to survive and thus serve as a site for crystal growth or crystal formation. This is a critical process in food preservation. So refrigeration is now the process by which heat is removed from a confined place and material for the purpose of maintaining a lower temperature. We have the units of refrigeration either as Fahrenheit or degrees Celsius. Yeah. Then we have several methods of quick freezing by direct contact with the refrigerant or by a blast of cold air or direct immersion in a refrigerating media. So freezing by direct contact with the refrigerant, food may be frozen by being placed in contact with the metal surface, which is cooled by a refrigerant or packaged in a can or cooled by immersion in a refrigerant. Also, food packaged in paper boxes may be frozen by contact with refrigerated metal plate, which may be moving or even stationary. Air blast freezing to obtain very cold air. A blast of air is directed through refrigerating coil, and for greater effect, the cold air blast is confined in an insulated tunnel. The material to be frozen may be placed in a moving belt within a variable of moved counter current and the air blast so that it's moving against the current that is cold. Then freezing by direct immersion. Um, in low temperature drying was the beginning of quick freezing. So since liquid are good heat conductors, a product can be frozen rapidly by direct immersion in low temperature liquid, for example, brine and sugar solution. So you place your food in brine and sugar solutions. So freezing time usually it depends, and it's difficult to determine the freezing time since freezing will occur at different rate for different types of food. The freezing will be faster at some point on the surface and in the body uh, of the piece of the food. Then there is a point that will cool a bit slower. So the highest temperature at which ice crystals have a stable existence in food material is known as the freezing point of that material, when we are able to have stable ice crystals. Because of the nature of materials of food and the presence of water-soluble constituents, all water does not crystallize at this temperature, and this is known as cryoscopic effect. Yeah, so those are uh, the various concepts that we have in industrial processing of food. We said food is the example. So we looked at material and energy balancing, preliminary operations, mechanical separation, membrane separation, contact equilibrium separation, and food freezing. If you have any questions, kindly channel them through the email